Hello everybody, still happy Friday. It's not quite good morning anymore, I'm sorry about that. But welcome back. I thought we'd talk about function behavior, a little bit of loose ends on section 3.1. And in doing so, we're going to be talking about increasing. These are all dichotomies, by the way. Increasing versus decreasing. Maxes versus mins. And actually inflection points, concavity. Now these are big words for calculus, and that's why we're doing this right now. And we're going to do one example, and most of this is intuitive. And by the way, in chapter 1 in calculus, the end of next September, you're going to be studying these three things quite extensively. So prepare for that. But here we go. I have, I'll bet you may or may not have ever seen this equation. It doesn't matter or not. This is what's called the normal distribution. And there's those of you who have had statistics. So the curve looks like this. Whoops, I missed. Close anyway. The curve looks like that. And this is the function. And you've had statistics, maybe or maybe not, but a point is pi is the number pi. Sigma, this is the standard deviation. E is the number E. Mu is the mean. Sigma, again, standard deviation. That's the variable right there, x. So the function value at x that's what you put it. If your function value at 5, you'd put it in right there. Whether or not you've ever seen this, that's the equation for the normal curve. So here's the normal curve right here. And so increasing from here on up, the function is increasing. Because for every x, f at x gets bigger. It gets bigger each time. Maximum. Huge calculus concept, a maximum and minimum of a function, and then decreasing down here. And that's all I'm going to say, except, let's just draw something, and concavity, sorry about that. This is important, it's not part of pre-calculus. This is next semester, you'll get this in chapter 3. Concavity means, these are called inflection points. From here to here, it is concave down. It means it's like a rainbow, a umbrella. And then this inflection point from here to here, it's called concave up. By the way, people who sometimes will draw a normal curve, they'll draw a normal curve, they'll do it like this, and it's all fine and good, but that's not right. Because that would be a minimum point, and there'd be inflection points right there, and the concavity would change. The normal curve actually is asymptotic. So that's it for behavior of functions. The rest intuitive. Please, if there's more you want to know, let me know. Okay, so now section 1.4. We're going to keep this simple too. It's called compositional functions. Composition of functions. Composition of functions, and essentially you put a function into another. Put one or more functions into another. Oh boy. If we have two functions, f and g, which I'm going to do, the rest of this is just examples. F at g at x means I'm putting g at x, whatever that is, into the variable for f. This is also, by the way, fog at x. Fog at x. I mean, we do it so often, we even, we call it fog. We don't call it fog, but that's the way you spell it, fog at x. So, for example, 3x plus 1, x squared plus 5. So, for example, 3x plus 1, x squared plus 5. So, for example, if f at x is 3x plus 1 and g at x is x squared plus 5, we can do all the following stuff. We do it all, right? we can do f at g at x, which, like I say, in our notation, fog at x means I'm putting this function right there. So this is 3 times x squared plus 5 plus 1. And then you do some algebra, which is 3x squared plus 15 plus 1. There you go. FOG at x. Whereas, by the way, you can do it the other way, of course, g at f at x, which is GOF. What I'm doing now is taking 3x plus 1, I'm going to put it right there. 3x plus 1 squared plus 5. Yeah, 3x plus 1 squared, 9x squared plus 6x plus 1 plus 5. 9x squared plus 6x plus 6. GOF at x. FOG at x. Just putting one in for the other. Now we can do that with variables as well. For example, completely different functions here. I considered naming these something different, but I'm going to use f and g. By the way, you can have 3, you can have 5 functions. You can have as many functions as you want. F, G, H is usually what we do. But here, another function, f at x, another example. 3x plus 1x squared plus 5. Oh, that was 1. So this is 3x squared, x minus 5. G at x, x minus 5. Boy, that's similar to that. Oh, shoot. I didn't mean to make that so. Well, and I'm going to erase these because this is a different example. We now have a completely different example. Sorry, they're so much similar. Me making up stuff. But my point is, we can do f at g at x, we can do f at g at f at x, or we can go FOG at a unique point, such as -1. This means f at g at -1. So if you work in parentheses, we're going to get g at -1. G at -1 is -1 minus 5 is -6. And then what we want is f at g at -1, which is f at -6, which is, 3 times -6 squared. 6 squared, 36, times 3 is like 108. Woof! So that's FOG at -1 is 108. And let's go backwards then. I got it at, at 2. Let's go GOF at 2. Last example, by the way. GOF at 2. That means I'm finding f at 2. Function value of 2 is 3 times 2 squared. 3 times 2 squared is, that's 4, that is 12. So then I'm going g at 12 is 12 minus 5. 12 minus 5 is 7. So GOF at 2 is 7. One more thing. GOF at x. What is that? I'm putting f at x into GOX. So this would be 3x squared, boom, minus 5. And then, so if I put this 2 in here, GOF at 2, well, we better get 7 or I have to start this table over and I made a mistake. So it's 3 times 2 squared minus 5 is, oh yeah, boom, 7. We are done. Hey, see you next time. Adios. Happy Friday.